So we looked at the hydrogenation catalytic cycle last week, right? When we started with an alkene, we add hydrogen to an alkene and we produce an alkane, all right? The catalytic cycles, they all look the same. So we all start with a catalyst, obviously whether it's homogeneous or heterogeneous, it doesn't matter. And then we add all of the different components of the reaction. At the end, we obviously produce we regenerate the catalyst, and we also hopefully generate the product, right? So every catalytic cycle looks the same. We'll start with the catalyst and then we go around, right? And we form pretty much a catalytic loop. Well, it's the same thing here that is happening with the hydroformylation or OXO process. Hydroformylation is an industrial process that allows us to start again with an alkene, but then we add not just hydrogen to it, but also a source of carbonyl, which means that we obviously are not going to have the production of alkane, but we'll have the production of aldehydes. Right? So if we think about what the products are going to be, and I'm saying are because they are going to be two different types of aldehydes produced no matter what we do. We can't prevent just the formation of both the branched and the linear aldehyde. So remember when I introduced this unit to you and I went over some of the very important terms, we talked about the regioselectivity, which is based on the stereochemistry, and we talked about the normal or linear to branched ratio of aldehydes. Well, that's exactly what's important here. We need to find a catalyst that is regioselective, that is not only efficient but also regioselective, so that we have more linear than branched aldehydes depending on the application. So if we are in the pharmaceutical industry, we would rather have branched aldehydes. If we are in the detergent industry, we would rather have the formation of linear aldehyde. But it's impossible to just have 100% linear or 100% branched. You're always going to have at least a few percent of the other kind of stereoisomer, even if you have the most regioselective catalyst available on the planet. Okay, so what we need to start with here is that we need to start with pretty much predicting the products, looking at what the products are going to look like, and then we'll start going through the different steps. So branched and linear aldehyde, the only difference is that you're obviously going to have some branches. The functional group is not going to change, right? So if we start with an alkene, right, so carbon-carbon double bond, and our group here on my alkene, I add hydrogen and I add carbon monoxide or a source of carbonyl, I'm going to end up with, right, so here my linear aldehyde, R, and then obviously my two carbons, right, and then the functional group for aldehyde is just a carbon doubly bonded to an oxygen and then a hydrogen. So this is my linear aldehyde. Additionally to that, I'm going to have the formation of a branched aldehyde, which means that here and I'm going to show you how obviously both of those are formed. But instead of having a CH2CH2, right, the hydrogen from the H2 will actually go on a CH2 to form a CH3, so a branch on that carbon, and then my functional group will still be present. Okay, all right. So the only thing that I really would like to point out right away is that if you start with an alkene, right, that has 1, 2 carbons, for example, you notice that in your aldehyde, because of the presence of the functional group, right, for aldehydes that has a carbon in it, you will not just have 1, 2 carbons. At the end, in each of the aldehydes, whether it's linear or branched, you will have 1, 2, 3 carbons, right? So by forming an aldehyde, you are increasing the number of carbons by 1. Okay? All right? So I can't show you in the same cycle the formation of the linear and the branched, because it's really getting very complicated. Because at one point, right, there's a kind of a different step that is taken that will lead either to the formation of the linear aldehyde or the formation of the branched aldehyde. So I'm going to show you here how we are forming the branched aldehyde, and then I'll show you how we're forming the linear aldehyde and where the steps are taking a different direction. Okay, one of the most common catalyst that is used to convert alkenes to aldehyde is usually based on either cobalt or rhodium carbonyl catalysts. So the precursor to the formation of the cobalt catalyst used very commonly in hydroformylation reaction is based on this dimer here, which has 2 cobalt, 8 carbonyls. Then when hydrogen is added to it, it actually forms something that you guys are familiar with. Right? It forms a cobalt catalyst with obviously a hydrogen, and we need 2 of these species here, and 4 carbonyls. Okay, so that's a neutral, obviously complex, but when you count the total number of electrons in here, right, we can't really add anything to it because it already has 18 valence electrons. So what's happening is that this precursor, right, that's my precursor. When it reacts with hydrogen, it forms this complex. But this complex here has to lose a carbonyl to be able to form the actual catalyst. So the actual catalyst here, which has 16 valence electrons, is based on cobalt with 1 hydrogen and then 3 carbonyls. So this is the active species, the active catalytic species. Okay, so that's what I'm going to be using here in the middle of my page as the catalyst. So remember, we need to make sure that we start in the middle of the page. We have enough space here because we go obviously in a circle. It's a cyclic catalytic, obviously it's a cyclic reaction, right? We start with a catalyst, at the end we hope we will regenerate it, right? So here we go, we have our tetrahedral species. It has 16 valence electrons. Step number 1, we have many different components here that are involved in this formation of the aldehyde. So one of the things that we need to take into account, right, is that we need to add the alkene, we need to add the hydrogen, and we need to add the carbonyl, right? Otherwise we won't form any aldehydes. So the first thing that is happening here is that we're going to be adding the alkene, right? So we're going to add here of the eta-2 alkene. Okay, so when I'm going to add my alkene in an eta-2 manner, I'm going to form obviously a species that is going to be trigonal bipyramidal. Okay, and this obviously component here, this molecule has 18 valence electrons. It's trigonal bipyramidal, 18 valence electrons because we are adding the alkene in an eta-2 manner. Okay, the rest of the molecule doesn't change. And it's actually the next step that will either lead us to the formation of the branched or the formation of the linear aldehyde. What I mean by that, because we have an 18 valence electron species here, we can't add anything else, but we know we still need to add the H2 and the CO, right? So what do we do in this case? What we do is that we need to make sure, right, that we end up again with a 16 electron species. So what's happening here, it's a hydrogen migration. So this hydrogen here is going to migrate, but where is it going to go? Is it going to go on this carbon here at the top or this carbon here at the bottom? And that is what is the main difference here in the formation of the branch versus the linear. So depending on where this hydrogen is actually going to migrate, we're either going to have the formation of a branched or a linear aldehyde, right? So the step number 2 is the hydrogen migration and the alkene insertion. So what I'm going to show you here, right, is the formation of the branched aldehyde, and then I'll show you how the linear aldehyde is formed. But the critical step here is right here. So this hydrogen here can go on this carbon, or it can migrate on this carbon, right? So if it actually goes on this carbon, we'll now have a CH3, right? That will be at the end of the group, right? And we'll still have a CHR. So if we actually draw what the resulting complex will be, right? We'll then have obviously a CH3, right? And then my cobalt will be still connected to the CH and R group. So we'll have CHR and then the CH3. Okay, so we'll go back to the tetrahedral complex that we started with, the same molecular geometry. This has 16 electrons, right? But as you see here, I now have a branch, right? I have an R group here on that carbon. Because I have a branch here, this will lead us to the formation of the branch aldehyde. Okay, and I'm going to call this step 2 prime, and I won't draw it here because I don't have enough space, but I'll show you. If we did not have, right, the hydrogen going on this carbon, but it would be on this carbon, right, we'll then have a CH2 CH2R, right? So if we actually would draw our resulting tetrahedral species with my 3 carbonyls here, we'll have, instead of having CHR CH3, we'll have CH2 CH2R. This is a linear chain. This will lead to the formation of the linear aldehyde. Okay, so I'll show you on a separate page how this would look like. So let's continue with our third step. Now we have a 16 electron species to start with. What else do we have to add? Well, we have to add our carbonyl and our hydrogen. So we add our carbonyl here, our CO, right? Where is it going to go? Well, there's a good chance that it's going to actually go, right, over here. It's going to be attached to the cobalt and it will form a trigonal bipyramidal species, right? So everything else stays the same except the shape. Okay, this, now that we've added a carbonyl, has 18 electrons. So we can continue, obviously, but we can continue by adding, right? We need to add our hydrogen, but we can't add it before we move on. So the only thing that we can add when we are stuck like this, right, is to do our migration. And remember, we talked about hydrogen migration, but we also talked about alkyl migration. And this is exactly what's going to happen here. I'm going to have an alkyl migration and a CO insertion in my 4th step. So my 4th step is an alkyl migration and a CO insertion. So before my carbonyl can actually be inserted, it's going to have, the molecule here will have to go the alkyl migration, right? So what the resulting product will be here is my CO, right, that has been inserted, and then I still have the rest of the molecule here. I have CHR and then CH3. Okay, just like that. Okay, so you can see here, right, that the aldehyde is kind of more obvious, right? The formation of the aldehyde with the branched here is a lot more evident than we had when we started this cycle. So we are not completely done, right? Because we still need to add our hydrogen. And so our fifth step here is the oxidative addition of hydrogen, right? So the two hydrogens are going to be added on my tetrahedral complex, which means I'm going to form an octahedral species. And then I have all my carbonyls. Okay. So we see here, right, the formation of the aldehyde. So remember, an aldehyde has a carbon doubly bonded to an oxygen and then a hydrogen, which happens to be right here in the cis position, right? So this hydrogen is obviously going to migrate to form the branched aldehyde, and I'm going to regenerate my starting material, which is my catalyst. So in the sixth step, right, I'm going to have a reductive elimination of the aldehyde. And my reductive elimination of the aldehyde obviously means that the hydrogen here is going to migrate on this carbon. So I'm going to form my aldehyde functional group here, and then the rest of the molecule. And then I'm also going to regenerate my starting material, my precursor. Okay, so we start with our catalytically active species. We add our alkene first in an eta 2 manner. We have a hydrogen migration, alkene insertion to go back to a 16 electron species. Then we can add our carbonyl. We add the carbonyl, we do an alkyl migration and CO insertion, and then we still have to add our H2. When we add our H2, it's really, the bottom line is that now we need hydrogen because otherwise we have a missing piece in our aldehyde. The hydrogen will migrate, we have a reductive elimination of the aldehyde, and we also recover our starting catalytically active species. Okay, the determining step here, in the sense that we either are going to have a branched aldehyde like here, or we're going to have a linear aldehyde, means that, you know, where this hydrogen here goes, right? So if this hydrogen goes, as we mentioned here, right, if it goes on this carbon, we have a CH3 here. If it goes on this carbon here, we have a CH2, CH2R, okay? So let me just show you here very briefly how it goes when we do have the formation, obviously, of the linear aldehyde. So when we start here with this species, the CH2, CH2R, right, and we do so it pretty much produces something that we have here, right? So that's the result of that the hydrogen migration and then the alkene insertion. So we end up with a species that can then have the CO attached to it, right? So when we have the CO attached to it, we end up with a molecule that looks just like this one, but the carbonyl is now attached to it, right? So let me show you how this works. So we have our CO. Now we have a carbonyl, CH2, CH2R. Just like that, right? So this will be the result, obviously, of the step number 3 when we add the CO, okay? All right, so as you can see here, right, what's going to happen is that I'm going to have the same step number 4, my alkyl migration and CO insertion. tetrahedral species, right? So here we have our carbonyl, C doubly bonded to the oxygen, CH2, CH2R. Okay. Then what else do we need to do? We need to add our hydrogen, so our H2. So again, the step number 5, right, is the oxidative addition of H2. Okay, so as you can see here, right, our reductive elimination is going to happen. We're going to have the hydrogen here migrate to the carbon. So we're going to have a reductive elimination of the linear aldehyde. My linear aldehyde here, right? We have our group, CH2, CH2COH, the functional group for aldehyde, and I'm still going to be regenerate. I'm still going to have obviously the catalytically active species here regenerated at the end. Okay, so in theory, right, this all happens really perfectly, but in practice, I'm sorry. I apologize. In practice, it's not that easy. In theory, it looks like it's a perfect cycle, right? And everything just works perfectly, and we have the formation of branched and linear aldehyde, right? We cannot have one without the other. However, there are some complications, and the reason why we have some complications is that, remember, one of the things that can happen whenever we start with an alkene, right? So remember, we start with an alkene, we add hydrogen, obviously we are going to have the formation of, alkane, right? We learned before the hydrogenation cycle, right? We start with an alkene, we add hydrogen, we form an alkane. So that's going to happen. The other thing that can happen is that you may have learned, I'm sure you have, that the aldehydes can also get hydrogenated to alcohols. So not only can we have the formation of alkane as side products, unwanted products, but we can also have the formation of alcohols. Okay, so it's unfortunate, but it is, the reason why we really want to have a catalyst that is not only regioselective, but also chemoselective, right? Remember when we talked about the regio and chemoselectivity at the beginning of this unit, we said that we really want to make sure that we have a much larger ratio of aldehyde, larger amount of aldehydes compared to the amount of alcohol produced, and that's why I said that at the time, right? We actually want to minimize the hydrogenation of aldehydes to alcohols because we want aldehydes, we don't want alcohols, we don't want alkanes, we want aldehydes. Okay, whether we want them branched or linear, that's another story. But the chemo and the regioselectivity really come into play in this particular industrial catalytic cycle. Okay. Just one last thing, the cobalt here catalyst is obviously the one that is mostly used, but there are also other catalytic active species such as, this one here based on rhodium and triphenylphosphine. And so one of the things that I would like to point out is that, remember, if you start with a species that has 18 valence electrons, you're going to have to remove a ligand first to give the catalytic active species, right? So you would have, in this example here, you would have to remove a triphenylphosphine ligand to be able to give a catalytic active species that only has 16 electrons, so that you can go back up here and have that rhodium complex and then add your alkenes and then go through the different steps in the cycle. Okay, so I hope, right, that what I really want you to be able to get out of this is to be able to not only know what the terms mean, but also go through the different steps associated with the hydrogenation and hydroformylation, whether it is leading to the formation of the linear or the branched aldehyde. I would like you guys to be able to get a good grasp on that. And then if you're interested, I obviously added some kind of additional knowledge there for you to know about what are we working on now in terms of the research in order to develop new homogeneous catalysts and new heterogeneous catalysts. All right, so this is how we're gonna wrap up the unit 6. I will post one more video on Wednesday, just kind of to remind you of what's important to know in this unit, as well as what is left to do here in this semester. And then we'll pretty much are going to be in great standing to finish the semester on a strong note. I'll see you later.